to Professor Watson from the University of the Witwatersrand, South Africa. He will present us some stochastic inequalities in Riesz spaces. Welcome, Professor. You can start.
Thank you. I would just firstly like to thank everyone who was involved in setting this up and all the work involved. And I should also note that this is based on work that has been joint work with Wenchi Kuo, the late Konrad Labuskaghni, and some of our PhD students who are David Rodder and Michael Rogans over the past few years. And this work was partially funded by the National Research Foundation of South Africa. I'll start with some very basic things. I want them for examples a bit later. So just to recall the probability space, it's a measure space where the measure of the whole space is 1. Random variable we take to be an element of the L1 space over the probability space. The expectation is just the integral of the random variable. And we can also consider an expectation as a map from the original L1 space onto the L1 space with the not quite trivial sigma algebra, but the one that's made into the AE version of that. Everything here, when we talk about elements of our L1 space, we don't mean functions, we mean the AE equivalence classes of those functions. And ordering on them is AE pointwise, they become vector lattices, etc. Dedekind complete vector lattice. Okay, conditional expectation operators. If we take a subsigma algebra of our original sigma algebra, we can form the conditional expectation operator on it by looking at the functions capital F, whose integrals over each one of the subsigma algebra sets coincide with the original function of which we're taking the conditional expectation, and we require that our capital F to be sigma measurable, capital sigma. The existence of the conditional expectation operator on L1 follows from the Radon-Nikodym theorem, and we also note that the conditional expectation operator maps from the L1 space omega F mu to L1 omega sigma mu. It is a surjection. It is positive order, and it's a positive order continuous projection, and it retains the constant functions as invariant. That motivated many years ago now our definition of a conditional expectation operator on a Riesz space. And we take an Archimedean Riesz space, as life is too hard if we don't, and we require a weak order unit on it. And we take a conditional expectation operator on such a space to be a positive order continuous projection, whose range is a Dedekind complete Riesz subspace of the original space, and which maps weak order units to weak order units. And it's easy to show, since it's a projection, it has at least one invariant weak order unit. We can also assume that such a conditional expectation operator is strictly positive. In other words, that if we have an element from the positive cone which is non-zero, then the conditional expectation operator of it should be non-zero. Otherwise, if that's not the case, we can always work in the quotient space. So that's the beginning of our setting for our work. And one note here is, if we start with classical L1 as our Riesz space, a classical L1 over a probability space, and we take a subsigma algebra of the original sigma algebra F, then the resulting conditional expectation operator on L1, which preserves the one function, is exactly the Riesz conditional expectation operator, and the converse is also true. If we take a Riesz conditional expectation operator, so we're considering positive order continuous projection on L1 that maps the one function to the one function on L1, then it is exactly a classical conditional expectation operator. And that the references to it in Riesz, the essential parts of the proof of that can be found in Douglas's work. Okay, next to our T universal extension. So we have a conditional expectation, and now we're going to take our life to a Dedekind complete Riesz space. And we look at an extension of that Riesz space that gives the conditional expectation operator its maximal domain. It's the largest extension you can make of the conditional expectation operator, which gives a conditional expectation operator on the resulting space and has the original space as an order dense subspace of it. So how do we go about this? We build the positive cone of it, that's called DOM T, and we look at the elements in the positive cone of the universal completion of E who have increasing nets in the original space, but which have supremum F. I recall that F is in the universal completion. It need not be in the original space. And we also require that the conditional expectation operator T applied to the F alphas are order bounded in the universal completion. And the resulting space E hat formed, the Riesz space formed from building it from DOM T is called the T universal completion of E, or that's what we called it. It has some very nice properties. It's a Dedekind complete Riesz space. The original Riesz space is order dense on it, and each weak order unit from the original space is again a weak order unit in it. And we denote the space E hat by L1T, as we will through the rest of this talk. The extension of the conditional expectation operator to E hat requires a little bit of care. Obviously, we can define it by taking an increasing net in E plus the positive cone of E, as was used to build DOM T, and which has T of F alpha bounded in the universal completion, and which has supremum F. Then the natural definition would be to define T hat of F to be equal to the supremum of T of F alpha. This is also a limit as well as a supremum in EU. Now, this exists, certainly. It also doesn't depend on which representative of F, which representative net we take. So it is well defined, and it can be shown that once we've extended this to the whole space from the positive cone, it is indeed a conditional expectation operator on E hat. It should be noted that these original ideas appear in the paper of Grobler and de Pachta, as cited below there. They were working in measure spaces, but the essential ideas are there. Now, the next step that one would like to look at is averaging. We need all of these properties to get to where we want to get to. So let's look back at the classical L1 setting. If we look at random variable f from our original space, and we take a set B, or sets A and B from our sub-sigma algebra, and we look at the integral over B of the characteristic function of A times the conditional expectation operator of f, we can obviously take that to be an integral of A intersection B. Now, A intersection B is in the sub-sigma algebra sigma, and so applying the definition of a conditional expectation, you can get that that is the integral of f over the intersection A intersection B, which can now be rewritten as the integral over B of the characteristic function of A times f. Now, so that gives us the first step of an averaging property. That says that you can pull characteristic functions of sets from your sub-sigma algebra through your conditional expectation operator. Now, this has an analog in the Riesz space setting, and that is that if you have an element from the positive cone of the range of T, and we associate, there's the band projection, we call it PG, the band projection generated by G, that will commute with T. So that is the first step on averaging. That does not require any multiplication type properties. That is a pure, it lives purely within our original space. Now, if we start to look at some of the nice spaces we've got L1, an L1 type space. We can define an L infinity type space by looking at all the elements of L1 whose absolute value is bounded by something from the positive cone of the range of T. And we can define general, it shouldn't have been between 1 and 2. P should be between 1 and infinity. I don't know why it's stuck between 1 and 2 here. LP, or as being the elements of L1 whose modulus to the power P is in L1 again, of T. And we, Kunrad, Guenchi, Michael, and myself looked at the cases of 1, 2, and infinity. Those were the ones that came from the problems in stochastic processes we were interested in. But Azuzi and Trewilsey did the general extension of this to all the possible cases of P between 1 and infinity. Now, there were some questions earlier about why we like our T universal completion. Well, if we work on the T universal completion, there's some very special things that happen. The first is that working on the T universal completion of our space, so in other words, E is L1T, then the range of T is universally complete. So we get for free that it's an F algebra. Further, that we then have that if U is an element of the range of T as a weak order unit, then it is invertible in range of T, and hence it has an inverse also in E. Next, we have that all the LP spaces are in fact RT modules. So you can multiply any element of LP by an element of the range of T and remain in LP. Further, L infinity with this definition is an F algebra. And further, the LP spaces are also L infinity modules. And now with all of this structure behind us, we can have a nice version of averaging. We have that the conditional expectation operator is an averaging operator in the sense that if we take any element F in the range of T and any G in our original L1 space, then F times G with F algebra multiplication is again in E, and T of F times G is F times T of G. Again, quite a few of these ideas can be found in the paper of Krobla and de Pachter cited earlier. Well, since we have that these spaces are RT modules, why don't we try and imbue them with some form of a norm? So that led us to the concept of an RT valued norm. So if we start with E being a Dedekind complete Riesz space with weak order unit, and we have conditional expectation, strictly positive conditional expectation operator on E, and we have further that E is an RT module, and phi is a function from the original space E to the positive cone of the range of T, with it being positive in this, or in the sense that phi of F is 0 if and only if F is 0. It's homogeneous on the positive cone of the range of T, in the sense that phi of GF is equal to the absolute value of G times phi F for all F in E and G in the range of T. And lastly, we have a triangle inequality. Then we will call phi an RT valued norm. And it behaves, the only difference is that RT is only a ring, it's not a field. Okay, well, these spaces, we're now in a position to look at norms on the LP spaces, and the easiest of them and the most natural one is the L1 norm, which takes F to T of mod F. The L infinity norm, which takes the infimum over the values in the positive cone of the range of T that bound mod F. And last, then the P norms, general P norms for P between 1 and infinity. These require the use of a functional calculus. And I see it's lost a, sorry, my space, my file has lost. There should be a T in here. I'm sorry, I was doing, there needs to be a T. So it should be TF, the norm of F with respect to TP is open brackets T mod F to the P, close bracket, to the 1 over P. There's a T missing in there. I will correct that when I upload the slides. Well, there we are. Sorry about that. Well, the next inequality, the first of the big inequalities, let's say, is Holder's inequality. And this can be found in Krobler's paper on the Jensen and Martingale inequalities, Jensen's and Martingale inequalities in Riesz spaces. And in Azuzi and Trebelsi's paper on LP spaces over Riesz, in the Riesz space setting. Okay, and this says that if we have F in LPT and G in LQT, then we certainly have that F times G is in L1, and the L1 norm of F times G is less than or equal to the Q norm of the TQ norm of G, and the TQ norm times the TQ norm of F. Well, let's see what we can do with that and where it leads us. The next result is a simple application of that, but it's a useful one. If we take the product space of n products of the Riesz spaces L1T with component-wise ordering, we can define a conditional expectation operator, blackboard bold F on this, and all it does is average the terms and pop that back into each one of the components. Then we can apply this, we can apply Holder's inequality to this setting from the previous slide, and we get immediately the summation Holder's inequality given here for finite sequences xi from LP, yi from QT, LQT, And this will prove rather useful in a few moments. Amongst other things, it gives us that these LP spaces form a scale. So LQ is contained in LP for P less than or equal to Q. And we have that the P norm of G is less than or equal to the Q norm of G if G is in LQ. Well, now let's start looking at some processes and try and put the pieces back together. So this is an example that is in the paper with Michael Rogans, Wenqi Kuo, and myself on mixing. We take it the next few steps and actually show how the mixing works in this. But the question of how this works actually appeared in the 3-volume series by De la Charie and Meyer. And they started looking at what they call spaces of sigma finite processes. And for this to be non-trivial, we need to take measure space omega a mu, where mu is a sigma finite measure, and with the measure of the whole space being infinite. Otherwise, it's not interesting. And we break up the space omega into the omega i's, where it's a measurable mu measurable partition, each with finite positive measure, each of the omega i's. And we're going to take as our original space E the L infinity omega a mu, with the conditional expectation operator on it relative to this partition A naught here. Sorry, it seemed to get lost. A naught is the sigma algebra that is generated by the omega i's. That averages over each one of the omega i's. And we can explicitly write out this conditional expectation operator as in Formula 2. So it's constant on each one of the omega i's as given there. Now, in this case here, because it's a very simple example, we can form the universal completion. The universal completion consists of equivalent classes of A measurable functions. The T universal completion of the space consists of these functions, these measurable functions, the integrals whose integrals over each one of the omega i's, integrals of the absolute values of them, is finite over each one of the omega i's. In other words, f restricted to omega I is in L1 for each I. This conditional expectation operator can be extended to L1 as a conditional expectation operator on L1t. The space has a weak order unit, the identical one function on omega, which was a weak order unit in our original space E. And the range of the conditional expectation operator consists of the functions which are constant on each of the A constant on each of the omega i's. And we can write out the L infinity space, what the L1, what the one norm and the infinity norms look like. We can do all the other ones as well. But what is noticeable here is that L1, classical L1 is not equal to L1t. L infinity classical is not equal to L infinity t. But we do have the scaling of the spaces that L infinity t is contained in L1t, while L infinity omega a mu is not contained in L1 omega a mu. Now, Koos-Krobler gave the following version of Jensen's inequality, and that is that the conditional expectation operator of G applied to F is greater than or equal to G applied to the conditional expectation operator of F. Needs a little bit of unpacking. F is an element of our L1t space. G is a convex function on the reals, who when we define by a functional calculus g of f and g of t of f, those must both be in L1T. Now, using the inequalities we have so far, we can build Clarkson's inequality for the case of for p between 1 and 2. The case of p equals 1 and the case of p equals 2 are trivial to do. P equals 1, there's nothing to do. And p equals 2 follows directly from the fact that the square of, p equals 1 is triangular inequality, p equals 2 follows from the fact that the absolute value of the square of the absolute value of f is the same as f squared. So how do we prove this? Well, this is the only proof I'm going to do in this talk. We take g of the Jensen's inequality applied to x to be equal to x to the 2 over p. This has the required properties because p is between 1 and 2. We take our conditional expectation operator to act on the product space given here. It's just a product of EU with EU, the space F, with component-wise ordering. And our conditional expectation operator just averages the two components. We can apply Jensen's inequality, and it gives us the second last inequality here, which when we write it out, gives us the last inequality on the page. Now, taking this inequality and substituting in a equals x plus y and b equals x minus y, we have this first long inequality on the page, which we can expand a little bit using our knowledge of squares. We can now apply the infinity case of Holder's inequality on the space F with the conditional expectation operator as given on the previous page here. And that yields the inequality in the middle of the page. We need to, if we interpret what the suprema means here, we have it, and we can bound that in terms of the sum of absolute value of p plus absolute value of x to the p plus the absolute value of y to the p to the power 2 minus p over p, as given in the second last formula on the page. Now, if we take the result of Holder's inequality in the middle formula and we compute the left-hand side of that, we obtain the left-hand side of the bottom equation, and we've already obtained the right-hand side. We now combine that with the top equation on the page, and we have Clarkson's inequality. Azuzi and Ramdani gave Burkholder's inequality in the Riesz space setting. And now I know my time is almost up. If we combine all of these pieces of machinery that we have there, and we look at we can define a filtration in a Riesz space by conditional expectation operators, adapted sequences, and sub-martingales, then combining a whole lot of these inequalities, we can prove the Hajek-Renyi-Chow maximal inequality as given here for sub-martingales in L1T. And as a consequence of that, one has a strong law of large numbers. And if one has the energy, it also yields a sub-Martingale convergence theorem. And we can also obtain one last thing that I would like to say. I think I have 1 or 2 minutes left. Is that right? We can define a mixing coefficient. So if we have conditional expectation operators U and V on our original space, which are compatible with T as described here, we can measure the degree of conditional independence of U of the spaces generated by U and V by what's called the strong mixing coefficient, as defined here. It's one of the many mixing coefficients that can be defined. And by using what we have, the inequalities we've built so far, one can prove the so-called strong mixing inequality for it, as given here. All of these have conditional, if one takes them back to the probability space setting, they have interesting conditional versions. They yield interesting conditional versions of the strong mixing inequality. You can also do uniform mixing, a whole lot of other mixing type results as well. Thank you.
So thank you very much, Professor Watson, for this interesting talk. Are there any questions or comments?
None. Is that good or bad? I'm not sure.
Bruce, I think that the idea of the group of Clarkson inequality here is different from the idea in the thesis.
Sorry?
The idea,
yes, it is. It's different from the one presented in the PhD student. Yes,
yeah.
The PhD thesis. This one uses, we have so many wonderful inequalities lying around that we have. One can work really efficiently. One doesn't have to work laboriously. Between Jensen's inequality, Holder's inequality, Burkholder inequality, you have an immense wealth of machinery that enable you to work really efficiently and produce nice results.
Which one is published?
The version of the proof of Clarkson's that I gave here is the version that's published.
Okay.
That the idea for that proof came from a paper by now I have to look it up. Parfanasamy, I think it is. And anyway, that the inspiration to do it as an efficient application of inequalities. So, but once one has Clarkson, one can get to the Hajek-Renyi-Chow inequality quite efficiently as well. So.
Okay.
So any other questions?
Yes, I have a question. Hello, Bruce. Thank you very much for a nice talk. And I would like to ask, is there any research about some kind of Doob-Martingale convergence theorem on Riesz space case?
Sorry, sub-Martingale convergence theorems. Well, there are. We published a paper on well, we only worked in discrete time, but we did some work on Martingale convergence, and it has some relationship to sub-Martingale convergence. And the work with Rodder has some results on sub-Martingale convergence for discrete time as well. We did produce an upcrossing theorem many years ago, which does give you access to convergence results as well. But the interesting thing with the Hajek-Renyi-Chow maximal inequality is it gives you a way to get convergence results without resorting to upcrossing.
Yeah.
So it's easier to get there, let's say. Upcrossing is hard work in a Riesz space.
Right.
So.
Okay,
Hi.
thank you.
Hi, Bruce, and thank you for this wonderful talk. I have a question. Did you plan to apply all of these inequalities to financial framework?
No. we built them as many of these inequalities have been built by other people. We've pulled them together to get nice results out. But no, we haven't tried applying them to anything in finance or economics. My knowledge of finance and economics verges on zeros.
I have another question, not exactly related to inequalities, but you speak about upcrossing the theorem. It's an important result. I thought for a long time of an upcrossing theorem, but with Martingale, with process indexed by general set, not by n or by r. So Grobler had built a result on for continuous case.
So that takes you to, if you're going to index them, or you're indexing them on stopping times then, or what?
No, you index by a net, not by. There is some work done in classical case for Martingale indexed by net, and there is a very nice proof of Radon-Nikodym theorem by Martingale. So
yeah,
it's the converse. So.
Okay, that's, as I said, our work has been, other than some of the Markov stuff that we did, which we did on nets. We did some stuff on nets there and things like that. We've done some work, we've indexed on stopping times, but those have also been discrete time stopping times. So our work has been exclusively on discrete time, other than one or two minor pieces, which, but not on the Martingale theory. So Koos is the guy who's done most of the taking over to continuous time.
Okay, I tried to produce an analog result for Martingale in Riesz space, but the upcrossing theorem has been difficult. I didn't.
I can share with you a copy of the upcrossing result. It was published years ago, about 15 years ago.
Yeah, I know it, but I speak about upcrossing theorem for general Martingale indexed by a net.
By a net, that's going to be hard. Just from the technical details involved, it's going to be hard work. Even for discrete time, the terminology and technical details are cumbersome. I think it would be interesting. I agree. I certainly.
There is many elegant application for if we in the classical case, if we start by studying Martingale, and then we can deduce many results with nice and elegant proofs.
Okay, I will look at it. We must talk about it.
Okay. Thank
I
you.
think it's interesting. I think it's an interesting idea and worth pursuing.
Okay, thank you.
So any other questions? So thank you again, Professor Watson, for this nice talk. I want to thank all the speakers of this session and see you in 1 hour.
Thank you. Thank you very much.